Thank you. So thanks for all coming back after lunch, and thank you to the organisers for the chance to present and also the chance to be back at this amazing venue. So what I'm going to be focusing on for about 2/3 of my talk today is what I was asked to focus on. And so this is this idea that we can search for axions that are not the dark matter of our universe by repurposing searches that are looking for the dark matter of our universe. In particular, the idea will be that for certain axions that just exist in the spectrum of nature, they must have been produced at some fraction in the early universe. Our knowledge of early universe cosmology is such that we can't just turn their abundance to zero. However, when these axions are there, making up some small fraction of the dark matter, they will also contribute to the observables that we have that are looking for that dark matter, and so you can actually end up constraining them. And so this is the idea that I'm showing you, where these constraints I'm showing you here come from. One of the main goals of this section is to describe to you this in detail. And this is going to be based upon some work that I did with my fantastic collaborators, Kevin Langhoff and David Mezgin last year. But additionally, now that I have you all here, I can also talk about whatever I want. And so in particular, in the last third of the talk, I'm going to completely change topic and talk about something I wasn't asked to talk about, which is some work that I had more recently that I'm very excited about, which is showing that if you just sit down and carefully compute how to solve the simple harmonic oscillator, you can actually still find some surprises. And in fact, as I'll run you through, just solving this equation for the simple harmonic oscillator can actually have a significant impact on the sensitivity estimates that exist in the literature for axion haloscopes. So I'll say some words about that in the end, but of course that's not going to be my main focus. And just to emphasize for this part, this is with some other collaborators, with Jeff Draw, Stefania Gori, and Jacob Leadham. So let me start out by just thinking about what is going to be the fundamental motivation for the first part of this talk, and that is this axion coupling to electromagnetism. But let me not dwell on this anymore. Of course, I assume everyone in this room is perfectly motivated to look for this, or you would have be spending your time differently than at this GGI. So what I want to do now is I'm going to tell you about a new way of, thinking qualitatively of setting constraints on this parameter space. So as we're looking at this, I just want to review where the basic constraints come from so far, and in particular, slowly run through the logic that builds up to the existing constraints we have on axions that just exist in the spectrum of our universe, these non-dark matter constraints on axions, because these are the ones I'm going to want to extend. And of course, like everyone else essentially in our field, a lot of what I'll be doing here will be drawn from Kieran's amazing GitHub reference. So to begin with, I think broadly, obviously this is somewhat of an oversimplification, but most of the bounds that we have on axions that are not the dark matter of our universe come from the fact that we think that they could be emitted from compact objects like stars. If these objects just exist in the spectrum of the universe, they could be copiously emitted from the cores of these objects. And there's a huge amount of physics that goes into this that gives rise to all the different shapes I'm showing you here. And I'm sure I'm missing some of the latest constraints on this plot. But let me just start out by describing the one that probably most of you are familiar with. And this is the famous cast bound. And so what cast does, of course, is it looks for these axions being emitted from our own nearby star, the sun. But it doesn't just study the emission of these, it also looks for them directly. It pointed for many years an LHC dipole magnet at the sun and looked for these axions coming from the sun into this dipole magnet, converting into KV or X-ray photons, and then trying to see something at the other end. Sadly, it didn't see anything, and this is how they're able to set these very strong constraints that many of us have turned to when we're writing papers on axions. One thing I want to draw your attention to, though, is that notice that the cast constraints stop at some point. In particular, you can see that they're starting to parametrically decouple at masses around 10 to the minus 3 eV I'm showing you here. So you might ask, why are they turning off at 10 to the minus 3? There doesn't seem to be anything particularly special about the sun at 10 to the minus 3. It has keV core temperatures, so why is this dropping off? And indeed, that's correct. Actually, the reason why these constraints start decoupling at around 10 to the minus 3 is to do with the detection end. When we're looking for them on the surface of the Earth, we have an order meter length magnet that we're looking for these objects to convert in. And when the inverse of that length scale is comparable to the momentum mismatch between the axion and the photon, because the axion has a mass and the photon doesn't, then this mixing will start to become parametrically decoupling. And so that's exactly what you see here. But it already tells you if you want a way to extend these constraints to higher masses, you need to get away from this detection part, because there was no problem with the sun. At higher masses, the sun is still radiating axions. We just can't detect them using our magnet on the Earth. And so indeed, that's exactly what happens when you go to the horizontal branch limits, which by some numerical coincidence are essentially at the same value as the cast, although there has been some recent updates to those. And what you're doing with the horizontal branch limits here is you're just trying to understand as stars go from this process of burning hydrogen to helium, and then there are two different types of stars there, the red giant branch and the horizontal branch. By doing measurements of the ratio of the number of those stars in objects, you can set a constraint on how many axions are being emitted as you go up to this hotter temperature. And so there you're not requiring to detect the axion, it's just some observability of the number of stars that you see. And so then the cutoff only starts to occur once the mass of the axion is higher than the core temperature of these compact objects. So you can push much, much higher up in the mass scale, which is what I'm showing you here. But eventually you do cut off because you reach the core temperature of these objects. And so if you want to go higher still, you need to find objects that are even hotter. And in particular, some of the hottest objects we can exploit in the late universe occur in the form of supernova explosions. And so there's been some very interesting work showing how you can extend these bounds up here. And so just for this talk, I've decided to cut things at 100 MeV in axion mass. But if you went further still, you'd find that there are essentially no star emission bounds anymore. And in that parameter space, you have to find other ways of getting to very high energies. And that's what we can do in colliders or in terrestrial-based experiments. So that's what would come in up here, but I'm not showing that today. So that's the broad space of these star emission bounds that we have so far, but it's a very active space. In addition to a number of the lines I'm showing you here being somewhat recent, there's also been some very interesting ideas about what can happen in this space. One that I would draw attention to, because I think it's a really beautiful idea, is to go back to this example of where the axions are being emitted from the sun. Of course, most of these axions are going to be emitted relativistically coming out. But if they have a mass that isn't that different to the core temperature of the sun, you could imagine that a large fraction of these, or at least an appreciable fraction, could be emitted onto bound orbits. They won't have enough energy to get away from overcome the escape velocity of the sun. And if this is the case, then throughout the history that the sun has existed, you might build up a large density of these axions around the object. And then, for example, in these parameter space, you could look for these axions decaying and you could set some constraint on the existence of such a basin. And so this is where this additional constraint I'm showing you comes in here. And this is based on some very nice work by Ken Van Tilburg and Will Durocco and their collaborators in the last few years. And it just goes to show you that you can still come up with some very interesting ideas to extend these star emission bounds beyond what we have so far. And this will be very much in the spirit of what I'm telling you about today, which is another way of extending these bounds on axions that aren't dark matter. So now, if we make the additional assumption that the axion is dark matter, shock horror, we can get much stronger constraints on a lot of the parameter space, because there's now this enormous energy density of these states that we can draw on. So in particular, building off this idea that the stellar basin could be decaying, well, more generically, if axions are dark matter, those states could also be decaying. So through this interaction that I'm showing you up here, of course, the axion can decay to 2 photons. And because this has inverse mass dimension, when you compute the axion decay rate, it'll go as the mass cubed. And so for higher masses, this is much more relevant than it is for lower masses. And so indeed, you can see that these decay constraints become much stronger as you go to higher masses. So broadly, where are these coming from? Well, dark matter we know should be non-relativistic. So when it decays, you're essentially just going to get a line of photons at half the rest mass of the state. And so what you need to do is look for that line in various data sets that we've collected. You might notice there's an island down here I'm showing you in blue. This is just to give you a flavor of what's going on in an extremely biased way. And some work that I did a few years ago that was led by Josh Foster, who's in the audience. What we did is we downloaded the European Space Agency's public data that was collected by the XMM Newton telescope. This is an X-ray telescope. And if you note here, the masses I'm looking at are around 10 keV. So when that particle decays, it'll produce keV photons, which are in the X-ray band. So this is the correct data set to be using for this. We spent a lot of work analyzing it. Sadly, at the end of the day, we didn't see any clear signature of a line. What that meant is that just as a generic statement, we know that dark matter cannot be decaying too rapidly to these photons. So we could set a constraint on the lifetime of about 10 to the 28, 10 to the 29 seconds, more than 10 orders of magnitude longer than the age of the universe. Or in terms of what we're talking about here, I can turn this around and then set a constraint on the value of GA gamma gamma, which corresponds to this blue region I'm showing you on the bottom right here. So that's one example of how you can set constraints here, but all of the other constraints I'm showing you on dark matter up at these highest masses come from similar, just looking for a line at different energy scales. So that demarcates the boundary of this parameter space. If an axion is dark matter, it can't be too heavy and it can't be too strongly coupled to electromagnetism for the reasons I've told you about already. But of course, as we're going to hear about a lot through the GGI program, there's tons of parameter space where the axion could be dark matter. And in particular, we really think it could live somewhere along this orange line I'm showing you here if it's the axion that solves the strong CP problem. And then this is really the domain of the axion haloscopes, which are the instruments that are looking for the axions that make up the dark matter halo of our Milky Way. And if you're a strong believer that the axion mass is around this value here, then this is an incredibly exciting time because ADMX is cutting into the most interesting parameter space at the moment. At other masses, it's slightly more challenging. You can see where Shaft and Abra are at the moment. They're not yet getting below these star emission bounds, and yet they have to assume that the axion was dark matter. So you might think that this is a deeply pessimistic state of affairs. However, these instruments were really just proof of principle. They worked as expected. And so the idea is that as we build bigger versions of these instruments, what we hope is that they will be able to achieve the entire sensitivity that I'm showing you here in the coming decades. Now, of course, there'll be a number of challenges to overcome from doing this, but this is the goal, and to extend this ADMX search to a number of masses. Furthermore, assuming they can get over their recent challenges, the hope is that the IAXO collaboration in the coming years will extend the great work done by CAST into even smaller couplings that I'm showing you here, and also actually probe some parts of the QCD axion parameter space. And broadly, these are just two of many, many experiments that we've all been hearing about that could cover a lot of the parameter space I'm showing you here. So tons of excitement down here, but I'm not going to talk about this anymore today. Instead, what I want to do is zoom in on a part of the parameter space that otherwise, at least for axion dark matter, might not look so interesting. And the reason for this is because, as I said at the outset, I want to exploit these dark matter searches to set further constraints or potentially open up a new discovery channel for axions that aren't dark matter. Because these are such well-motivated particles, I think there's every reason to search for them, even if they're not dark matter. And of course, many of us are doing exactly that. So the heart of the physics here comes from the following very simple observation. Let's just imagine we have an axion that has a mass of around 10 keV. Well, you can see that if it's dark matter, I can constrain it significantly more than if it's not dark matter. Just for reference, let me just go to the horizontal branch limit here, because that's what I have a good value for, and that's representative of the size of the constraints around this mass value. It turns out that if you're a particle that lives up here, you are 8 orders of magnitude more strongly coupled than what we can already exclude for dark matter. So initially you might say, so what? It's not that shocking that once I've assumed this is dark matter, I can set a much, much stronger constraint. And it just turns out that it's 8 orders of magnitude improved over what I had previously. Of course, that's true. But just to think about where these constraints are coming from, they're constraints on the particle decaying. And of course, the decay rate is dictated by quantum mechanics. And so that's proportional to the coupling squared. So that says a particle that lives somewhere up around here will decay 16 orders of magnitude faster than the one that we can actually constrain down at the bottom here. And a corollary statement to that is that a particle that lives near the horizontal branch value for this mass cannot make up more than 1 part in 10 to the 16 of the dark matter, or it would be inconsistent with the constraints that are looking for dark matter. So that tells you cannot allow anything more than an absolutely negligible fraction of these states to exist as dark matter, or they're going to be in tension with what we've seen so far. And then you can ask, do we know enough about the early universe to determine whether there could be some tiny fraction of them here? Well, this is exactly the idea that we push forward, and the answer is yes. Of course, there's a lot more going on than the simple story I told you about here, but there is an irreducible fraction you can have, and so far, it is in tension with the dark matter constraints we have, and so this is how we're able to set these bounds here. But also in the future, it potentially opens up a new discovery channel to these types of states. So for the main part of the talk today, what I really want to tell you about is in more detail, how do I make quantitative the argument I just went through with you here. Oh, skipped over one. So in more detail, I'll just firstly give you a slightly more quantitative estimate for why I think this is an interesting way of searching for these axions. After this, I'll tell you in more detail how you can compute this irreducible abundance that should be there and why I think it's very conservative, the abundance that we're setting. From here, I'll tell you about how you can constrain this abundance, or in more detail, how we can draw on the various X-ray constraints, C and B constraints I showed you previously. I'll say some words about how I think this is a very generic idea. Today, I'll just be telling you about searching for axions coupled to photons, but this can be applied to other couplings and also other states. And then finally, I'll get to the last third of the talk where I'll talk about something completely different. So let me start out with this rough sensitivity estimate to why this is something you might even want to think about. So again, just to make life simpler before we do the full calculation, let's think about axions that have a mass of around 10 keV, because at least me personally, I'm very familiar with the dark matter constraints we have at that mass. So in particular, it's not a difficult thing to estimate, but nonetheless, let me just tell you, as a function of the coupling that you have and the temperature the universe reheated to, you can roughly estimate that the fraction of dark matter you would have if you're at the horizontal branch star limit would be about 10 to the minus 4 of the dark matter. So you can't have had a larger coupling than this. So for this value of T reheat, you couldn't have produced all of the dark matter this way, but you would produce some fraction of it. Now note, the actual process I'm showing to generate this abundance, there are many, I'll come back to them, is this so-called photon conversion. It's where a photon interacts with an electron or positron in the primordial plasma and the photon is converted into an axion. In different contexts, this is sometimes called Primakov, but of course this is something that can happen once Ga gamma gamma is non-zero. Of course, this process is UV dominated, so the amount of states you'll freeze in through this is going to be dependent upon how hot the temperature was in the early universe. I'll say some more words about this later on, but I think 5 MeV is an extremely conservative value to assume for this. So that's what an estimate of the abundance is. Now let me estimate what the constraints will be on this. I've told you already that at 10 keV, we know that the lifetime, at least Josh's hard work told me, has to be longer than about 10 to the 29 seconds, which I can convert into this limit on Ga gamma gamma, which, as I showed you, is already about 8 orders of magnitude below the horizontal branch limits. But I'm not trying to constrain dark matter here, so I need to think about how I can convert this. What I have a state that is a smaller energy density, but has a shorter lifetime, so it's decaying more rapidly. So if you think that through, what this state is going to have to satisfy is that its density divided by its lifetime must be smaller than the equivalent quantities that I have for dark matter. Now, the fraction is, of course, just rho A over rho dm, so I can get that out. And so that has to be smaller than the ratio of these lifetimes. And then recalling that the decay rate, which is the inverse lifetime, goes as the coupling squared, I can rewrite this again with an inverse as the coupling that I've been able to bound to dark matter over this new coupling I'm trying to constrain for just any axion state here. Good, so now I've estimated what is the abundance and what is my ability to constrain any arbitrary abundance as a function of the couplings. So let me just put these two things together. Again, I'm fixing the mass to be 10 keV. I'll do the more general case later on. And I'm fixing this reheat temperature to be 5 MeV. I'll say some more words about that also later. So if I combine these together, I know that this value here, which is the abundance, has to be smaller than what I've been able to constrain with these dark matter results, which is what I'm showing you here. The game is, of course, I want to set some constraint or some sensitivity to Ga gamma gamma. So what I want to do is move Ga gamma gamma to the left-hand side here. So let's do that. And note, just to keep this, rather than putting dimensions into this, let's just see if I can do better than the horizontal branch limit, because that's the whole game here. We already know what the horizontal branch constraints are. If I can't do better than that, then this isn't a very interesting thing to pursue. So I'll keep this in terms of a ratio with the horizontal branch limit. And so that will mean I'll need to multiply by 1 over Ga gamma gamma HB squared on both sides. And then if I move to this 10 to the minus 4 on the other side and account for the fact that now I'm going to have 4 powers of Ga gamma gamma, so I take the quarter power, I get this result here. Remembering that the current dark matter constraints are 8 orders of magnitude below the horizontal branch constraints, this value is 10 to the minus 16. So I've got 10 to the minus 12 to the quarter or 10 to the minus 3. Which tells me that I can already, with this idea, get 3 orders of magnitude below the horizontal branch limit at this particular mass, which suggests, at least to me, that I should sit down and do this calculation carefully. So that's exactly what we did. So let me first turn to a more accurate calculation of this abundance beyond just the simple estimate that I gave you earlier on. So to begin with, when I was estimating this earlier, I only showed you how to compute the abundance from this photon conversion process. But before I think about what are the relevant processes, let me come back to this other aspect of this, that I said that for that particular photon conversion, the production was UV dominated. So the amount of states you got was going to be dependent upon how hot the early universe was. So if I want to set some, I mean, of course, for parts of the parameter space here, you'll be comparing to certain different constraints, and people are often very they can be sometimes very cautious when you say you've got some constraint from the early universe. So I think the thing you want to do here is be as conservative as you possibly can. So if I'm saying that the abundance gets larger when I increase the temperature of the early universe, a natural question is, what is the lowest reheat temperature I could plausibly have without destroying all of the successes we've got from Big Bang cosmology, for example? And I think one of the greatest successes of our understanding of the early universe is, of course, Big Bang nuclear synthesis. And as has actually been studied in great detail, if the universe never got as hot as 5 MeV, BBN just wouldn't work as well as it seems to. It just wouldn't agree with the data. So we know that the universe at least had to have got to 5 MeV. Now, my theoretical prior is that it was much hotter than that, but this is at least the minimum temperature that I think we need to have. Otherwise, our picture of the early universe has massive holes in it. So in this picture, I'm going to take as a very conservative value to just assume that the universe was 5 MeV. And I can talk, if there's any questions about this, about how this picture might change as I made things hotter and hotter. Okay, so now let's imagine we have a universe at 5 MeV. And so we've got the hot primordial plasma. What are the relevant states that we have in there at that time? Well, of course, we've got photons, we've got neutrinos, and we've also got electrons and positrons. So if I'm only thinking about an axion coupled through electromagnetism, I need to ask, what are the relevant processes that I could freeze this axion in through when I have those states in equilibrium? And if you sit down, you can convince yourself that it's only these three processes you need to think about. There's this photon axion conversion I told you about. There's a process called photon coalescence, which I know there's only three processes, but this has often been overlooked in the literature. And then the final one is there's this electron-positron annihilation, which can also produce the axions here. These first two are UV dominated, this one is not, but we'll carefully account for that. Please. So for the, no, this is something for a given reheat temperature, this would be something you need to check in detail. What I'll have this number later on. For 5 MeV, where you would reach equilibrium will always be above the plot that I'm showing you here. But if you because these things are UV dominated, you might worry about this as you changed the reheat temperature. Yeah, eventually it'll just reach equilibrium. I don't, I mean, it's a function of what value of GA gamma gamma you have. So I have that expression, I think even somewhere in my talk, but I don't remember off the top of my head. But it's a detailed question. It's not just independent of GA gamma gamma, when would this happen? It's a interplay between the two. So no, it's a good point and something we did check for 5 MeV, but you need to think about it if you're impose a stronger UV prior on what you think the reheat temperature was, which is exactly right. Yeah. So let's just stick with this simple scenario to begin with, and this is exactly what was already being asked about, where we have the reheat temperature as 5 MeV. In this case, you can check that if the GA gamma gamma was bigger than 10 to the minus 7, of course, that's completely excluded by several orders of magnitude by horizontal branch limits, then you would reach thermalization, but not for the actual parts of the parameter space that we're going to be testing here. So in that case, what you would have is what's going to be very important when we're thinking about the abundance that you can generate is this mass when it's equal to T reheat. So I'm showing this as a red line here because for masses well above the reheat temperature I'm assuming here, we shouldn't expect to produce many of the states. They should be Boltzmann suppressed, it should be exponentially depleting. So this is going to be a relevant a comparison point in the abundances that we're computing. So it's a bit detailed, but it's not a calculation any different to what many of you have performed, I'm sure. And so you just sit down and determine what is the amount you actually freeze in for these specific processes for a given coupling and for this fixed T reheat. And so you can see if you live at values that are above what's already excluded by horizontal branches, you can actually produce order 1 of the dark matter from this. But where we'll actually be living for what I'm talking about today, I'll be living at much smaller values, these fractions I'm showing you down here. And in particular, exactly as you would expect, once you get well above this T reheat, the abundance starts to become exponentially suppressed. So that's for the photon conversion. The next process I'm going to talk about is this photon coalescence, where these come together to form an axion here. And you can see at lower masses, these aren't as relevant, but when you get to masses that are above the reheat temperature, actually these inverse decays stave off the exponential decay a little bit further. So they can be very important if you have masses comparable to the reheat temperature. So the fact that they're not always that relevant is maybe one reason people haven't always included them, but if we're doing this to be fully consistent, you need to put them in there. But one case you can completely safely exclude is these E plus E minus annihilations. They don't give any particular significant contribution to the abundance here. I mean, the plot's starting to get a bit messy here, but this blue is associated with FA equals to this one case here. And you can see that they're just giving a much smaller contribution than the others that I'm showing you. So again, because this state doesn't achieve equilibrium in the parameter space I'm showing you here, I don't need to worry about any back reaction processes. So if I want to know the total abundance, this is freezing in, I can just add all of these together. And so that tells me that the final abundance is just essentially tracking the lower value of this line here. And so you can see that it's at lower masses, it's dominated by this electron photon axion conversion, and at high masses, it's dominated by the coalescence, which is what I'm showing you. But nonetheless, through this procedure, what I can do is that for a given value of GA gamma gamma, in principle, for a given value of T reheat, I can compute, and a mass, I can compute what the abundance that I would actually have of these axions. So the more important question is, let's say that these are there, can we actually see them? And so now I want to turn to the question of whether you could actually search for these using these dark matter constraints I told you about at the outset. So let me zoom in on this higher mass parameter space I showed you earlier on. And again, I'm just considering axions that aren't the dark matter, so I'm not going to include the dark matter constraints. So here's where the horizontal branch constraints were I showed you earlier on, and then they cut off as the mass gets well above the core temperature of these stars. These are the nice basin constraints, and here are the supernova bounds I showed you. Additionally, let me add in two other results that people have considered in this literature. So just generically on these axions, if they've very high mass and they're very strongly coupled, some of them could be decaying during BBN. And this is a result that was worked out by these authors here a few years ago. For reasons I didn't fully understand, they decided to work at 10 MeV instead of 5 MeV, but I wouldn't expect the constraints to change very much. And you can see they were able to constrain this little island of parameter space I'm showing you here. And then you can also ask, well, if decays during BBN can be constrained, there can be some other very early epochs where we might be able to constrain decays. And one of the other earliest epochs we can measure is with spectral distortions. So as soon as the photons that eventually come to form the CMB lose chemical equilibrium, which is at redshifts of order 1 million, any decays after that will start to distort the spectrum of the CMB. And so these spectral distortion results are able to probe decaying particles at extremely high redshifts or extremely early times. I mean, not as early as BBN, but not much later after that. And what was worked out by these authors, including Sebastian Hoop, who was here until yesterday, was that you would get these constraints from spectral distortions that I'm showing you up here. So this was the parameter space that we want to add on top of using this abundance that I told you about. So let me put that abundance on. So indeed, in the parameter space that is currently allowed, nowhere am I getting up to large values of this fraction. However, I can get to very small values of the fraction, which is what I'm showing you here. And so in particular, remember that earlier on, if I was right up there, I couldn't be more than 10 to the minus 16 of the dark matter. You can imagine that I might get some constraints from this. So let's start to think through just roughly at a cartoon level, what I can do with this in terms of getting some constraints. And then I'll go and do this more carefully. Or in other words, let me tell you how I started out with this and how I slowly made this picture more and more accurate. So to begin with, the first picture you can do that is completely wrong, but let me put it through nonetheless, is let's just imagine that I can constrain dark matter decaying to photons at some arbitrary lifetime. I mean, some of you may be very familiar with this literature. If you're not, I can just tell you that roughly independent of mass, we can constrain lifetimes for dark matter decaying to photons at about 10 to the 28 seconds, so about 11 orders of magnitude longer than the age of the universe. So if you imagine you have such a constraint independent of mass, then this would, as your first guess, would be the constraint you'd be able to set here, because this fraction can't exceed this ratio of the lifetimes here, and so you get an amazingly strong constraint that only starts to cut off as your abundance gets exponentially depleted above the reheat temperature. So that would be fantastic, but of course it's missing a very key piece of the physics, which is that as I move to higher masses and larger couplings, this state is decaying more and more rapidly. And where are these X-ray constraints coming from? Well, for example, we're looking for dark matter decaying at the center of our Milky Way. Now, the center of the Milky Way might be 24,000 light years away, but it's not that long in terms of cosmic history that the particles that decayed there we're seeing today. So if this has an extremely short lifetime, you might actually completely deplete the abundance that you had at the time you're looking for these constraints. Or in other words, the flux you get from decaying dark matter isn't just 1 over the lifetime, it's 1 over the lifetime times an exponential factor, as you always have for exponential decay. But often in the decaying dark matter literature, this factor is neglected because if the lifetime is much longer than the age of the universe, this exponential is not giving you anything, so you can just drop it. But in this case, it is absolutely crucial because we can have extremely rapidly decaying particles. Because this is an exponential cutoff, it will come in very sharply. And I can tell you that roughly when the lifetime of this state is shorter than about 1/10 of the age of the universe, you really won't be able to see anything appreciable when you're looking for decays in the late universe, essentially. And so you unfortunately need to cut out all of this parameter space that I showed you up on the top right. So again, this is just a cartoon estimate for what you should be sensitive to. If you had a constraint that was roughly 10 to the 28 seconds independent of mass, but you need to do the exercises of determining what the actual constraints are. But it turns out it's not too different from the estimate I just went you through. In some places, we have constraints that are stronger than 10 to the 28 seconds, and in some cases, we have constraints that are weaker. In particular, what we're combining here to get this single orange blob was 8 different constraints on decaying dark matter, including the XMM one I told you about earlier on. But actually, this single blob that I'm showing you up here comes from some very recent constraints that came from a reanalysis of the integral data. So integrals now collected over 20 years of data, and in some work by Francesca Calore, Pasquale Sapico, and collaborators, they showed that you could set extremely strong constraints on decaying dark matter up here, and that's where these constraints are coming from. Another point of this you might notice is that these constraints are being cut off at lower masses. The reason for this is as this state gets lighter and lighter, you might think it starts to behave like warm dark matter. And if that's the case, you should be very nervous that I can just repurpose searches for cold dark matter using this warm state. And indeed, we were worried about this as well, but we checked that if you're until you're below about 0.1 keV, it does not really behave like warm dark matter. But just to be conservative, we cut off any constraints that we had down at this lower value here. And I mean, it's not that there's no constraints here, but you'd need to account for the different distribution of these states in galaxies as opposed to what cold dark matter has if you wanted to really make use of those results. Additionally, just to get a sense for how well you could scale this in the future, you can look for what if I had a constraint that was at the level of 10 to the... Yeah, please. No, go, yeah. No, so good, but warm dark matter clusters differently within the Milky Way. It will not have the same, say, NFW or whatever distribution you assumed as you move into the core. It will have a broader distribution. And as it gets warmer and warmer, you'll have a larger and larger core essentially forming this. And so some of these constraints come from looking for decays near the center of the Milky Way. Yes. But it's the only one you can see. Like I'm imagining here that the rest of the dark matter isn't decaying to photons. It's only this tiny subcomponent that is. But the spatial distribution of this will be different to the cold dark matter that I drew the constraints from.
No, yeah, but the dark matter is there now. So this warm dark matter, by the time it gets through enough, it's not the one that says
Good. No, good. No. You just maybe something that you're getting at that I'm being a bit blasé about. This doesn't behave just like warm dark matter. What it behaves like is if you have 90% cold dark matter and you have a fraction of warm dark matter, because the halo form is essentially the same, and this thing falls into the potential well of the cold dark matter. Yeah, it's not exactly like warm dark matter. You were correct on that. Luckily, I don't know if I had okay, I've got this in a backup slides. Gianfranco Bertone and collaborators in 2012 sat down and did n-body simulations for what if I have 90% cold dark matter and 10% warm dark matter? How does the thing... Yeah, no, thank you. No, I was being too blasé. You're exactly right. It doesn't behave exactly like warm dark matter, but still the subcomponent will not cluster exactly the same as cold does. Yeah. So they only went down to fractions of 5% in their simulations for reasons that only they can explain. Well, what if it decays to photons at a rate I'm showing you here? Yeah. No, but it gets very small. And in fact, actually what the Bertone paper showed was that as the fraction gets smaller and smaller, the distribution that they get in the galaxies becomes independent of the fraction. And the intuition for this that I took, although they didn't write this, I think what's going on there is that the potential is completely determined by the cold dark matter. And then you just have a test particle moving through. It's not having any feedback on the... Oh, no, there's no, if your point is that there's no constraints from like the matter power spectrum and details like that, I agree at these values. Yes, yeah. But if you could see this state because it decayed rapidly to photons, you could see it in terms of the different spatial distribution. And what we're being cautious about is that I can't just repurpose a constraint that assumed the cold dark matter distribution immediately to my result if it actually clustered differently. So that's why we were being conservative here, but we checked that for most of the mass range that wasn't an issue. Unfortunately, in the Bertone paper, they said in a forthcoming paper, they'll consider dwarfs, but 11 years later, that still hasn't appeared. But I hope that somebody does that as well. Yeah. There are constraints there from Leo T. There was a paper on dark matter decays heating up Leo T, and you can get some constraints on this. I forget the authors who did this. But for Leo T, at very low masses, this is one of the dwarf galaxies. I'd be very nervous that I can really just lift their results and take it off. So we just didn't even include it. So that we were being conservative in that sense. Yeah. No, thanks for keeping me honest. Good. Yeah, so just if you put some of, I mean, we actually included the warm dark matter, how that modifies that. If you can notice, there's a slope change down here. But if in the future from the Milky Way, you had constraints at the level of 10 to the 29, 30, and 31, you would get the bands I'm showing you here. So you can see you can improve on the lower end, but notice, excuse me, you cannot improve on the upper end. And the reason for this is because you're just putting another factor into this exponential. It's still happening very rapidly. You're not gaining very much. And so while we've got, these are the strongest constraints generally we have on decaying dark matter, we've been completely unable to probe a lot of the parameter space here. And so, but I've already told you why that is. It's because there's no states around to decay to look for this. But if I had some observable that was sensitive to the energy injections at earlier epochs, then I would be able to set some constraints on this. So then you can think, if there's a constraint that on dark matter isn't competitive necessarily, it could still be relevant if it was probing an earlier epoch. So just one way you can think about this. What if we consider all the decays that have ever happened throughout cosmic history? These will form a contribution to the cosmic radiation background. The photons will be redshifted until today. And as a very conservative constraint, you can just say, well, we've measured the cosmic radiation background at an enormous number of frequencies. Let's just not overproduce what we've seen so far. So this is not a compelling constraint on dark matter, but it is actually allowing us to constrain parts of the parameter space that we couldn't access otherwise, because it turns out that these constraints are relevant up to redshifts of about 20. For redshifts higher than that, you don't get an appreciable constraint on this part of the parameter space. So that's something, but it certainly hasn't filled in all the gap. But we can go back further still and use the incredibly strong constraints we have on decaying dark matter for measurements of the CMB and anisotropy spectrum. So we had to make a few assumptions to repurpose the results that we had here, although I claim we did them very conservatively. And this is the bound that we're able to get from the CMB here, and this is where we will be able to extend our sensitivity to with the soon-to-be available Simons observatory sensitivity. But you can see for a lot of these masses, if this was purely dark matter, it's the X-ray constraints that dominate. But here, actually, you have to use probes at different epochs to get after this state, just because it's decaying so rapidly. What are the lifetimes? Good. So we can figure this out, right? So I said here, where it's 16 orders of magnitude decaying faster than the constraints we have from dark matter. Dark matter is 10 to the 28. So the lifetime of the state right here is about 10 to the 12 seconds. So there's 1 point, and then you can scale the rest by massive. Yeah, good. Okay. So that was the, oh, Philip, please. No, these are good. There's different constraints you can get from the CMB. There are the spectral distortions, which probe extremely early epochs. That was the constraint I showed you up here. These constraints here are from decays that occur after recombination. You ionize some of the neutral hydrogen, and then the free electrons distort the propagation of the CMB photons to us. And so the constraints on that are the CMB anisotropy probes. And these are actually, in terms of the energy injections you can probe much smaller energy injections once you get to the anisotropies. Yeah, because even a few more free electrons can noticeably perturb the CMB spectrum that we see. They're extremely strong constraints. However, they only turn on for decays after recombination. So this is why spectral distortions can still be relevant here, because they're much weaker, but they probe much earlier epochs. However, I claim we didn't do the most detailed analysis of the CMB. I think there could be improvements if you actually did a dedicated analysis here, but we did not. So that was the main thing that I wanted to walk you through here, and I've left myself absolutely nowhere near enough time for what's left. So let me just jump through onto the next part. And to say you can readily extend this idea, I told you about the coupling to photons. You can easily extend it to the coupling to electrons. You can even, for example, talk about what if you had some misalignment contribution in addition to the freezing contribution? We didn't include this because although I think there should be some misalignment contribution, in principle, the initial misalignment angle could have been arbitrarily small. So I wouldn't claim it's irreducible, but it gives some interesting physics if you add that in. And you can also extend this idea to other states. We did sterile neutrinos in our paper. You can think about dark photons, gravitinos, etc. But I'll leave that for the discussion. Please. Yeah, of course. Yeah. Absolutely. Exactly. But by the same token, I also don't think the universe reheated to 5 MeV. So I'm just trying to think about what is the most conservative way I can constrain that. In the interest of time, I have a backup slide on the misalignment I can show you and we can chat about it, but I just want to say a few words about this topic here, which is about how to solve the simple harmonic oscillator. So one of the key results I have here that I want to review is something that is well known in the haloscope literature. I'd used many times, maybe some of you had used a lot, was the following scaling for how sensitive you should be to a given axion coupling as a function of your resonant instrument runtime. And so there was this very nice result in this one of the first papers to really tackle this in detail by Dmitry Budka and collaborators, where they claimed that for times much less than the coherence time of the axion, you go to the t to the minus a half scaling, whereas once you're longer than the coherence time of the axion, everything slows down and you get t to the minus a quarter. It's a result I've used many times and maybe you have as well. And just to remind you some of the basic details here, the timescale that's playing the core role here is the coherence time of the axion. And because this is we're treating it here as this, as dark matter and this wave dark matter. Sorry, 1 second, I'll just finish this and I'll come to you. This wave dark matter is cold, and so it's extremely coherent. And so for a mass of about a nano EV, we know it has a coherence time of about 1 second, which is very long for the types of processes you might look at those frequencies. And then the other thing to note here is that for those of you who come from sort of an electrical engineering background, you might be very familiar with the famous Dickey radiometer equation. So in a certain limit, everyone knew that this result had to reduce to the Dickey radiometer equation, this t to the minus a quarter. So this result had a lot of people nodding along because, yeah, I expected this to go this way. That's what Dickey radiometer predicts. But as I go to shorter times, I get a slight deviation. Please, Philip. Exactly, it could be, but I'm being generic here because this holds for an arbitrary haloscope. So this could be the coupling to nucleons, it could be the coupling to photons, so I'm just calling it a generic G. Thanks for clarifying. So what I'm going to tell you is that in a certain limit, this is true, but there's actually more physics to this story. And that is because you can't just compare two timescales. If you're thinking about a resonant haloscope instrument, there's another very important timescale that enters, which is the natural timescale associated with the resonance of this device. So for example, if you're talking about NMR, the natural timescale is T2, how long you can keep the transverse spins coherent. If you're talking about a resonant cavity instrument, there's a timescale associated with the power to be dissipated through the walls of that. If you're thinking about a Fabry-Perot cavity, there's a lifetime for the photons to live in that state. There's always some lifetime that you need to account for. And you can ask, well, where should I put that timescale in this problem here? And you find that there are 4 ways you can order it, and you get different scalings for the G as a function of these. And so this shows you that maybe in some limits, you might not be scaling as you thought. And in fact, in certain limits, you can scale faster. And so this tells you that you might actually expect some enhanced sensitivity to couplings at certain scales. So where is this coming from? Well, ultimately, as I'll show you, you really just sit down and solve the simple harmonic oscillator, and then all of these timescales fall out. I'll say a few words about this, but I'm also conscious I haven't left myself enough time to solve a problem even as simple as the simple harmonic oscillator. So just to tell you why the simple harmonic oscillator is the right problem to solve here, and I'll give you an example by turning to these NMR, because this is what originally got me interested in this problem. So what's happening with NMR is, I mean, maybe you've sat in one of these devices, but the idea is you have some bulk magnetization that you're trying to study the evolution of. That's what this M is here. And then the presence of an additional magnetic field will put a torque on these spins and so change the magnetization. But any change will be resisted by these 2 timescales. T2 is the timescale for the transverse spins to exponentially decay, and T1 is the timescale for them to exponentially go back to whatever the value you set by the external magnetic field. So why is this interesting? Beyond the fact you can do amazing imaging with this. Well, the reason is when you actually go and have an NMR, the way that they tip the spins, this B, this is provided by some pulse laser that you fire into the sample. But for axions, they can play the role of this pulse laser. An axion coupled to nucleons actually behaves like a magnetic field. And so it can sit in here and it will be trying to tip the spins constantly. And so this will, in the presence of this large external magnetic field, cause them to precess. And then you'll get an oscillating transverse magnetization that maybe you can read out with a very sensitive pickup loop. This is definitely not my idea. This was the beautiful idea of Budke, Graham and collaborators, which is essentially what leads to Casper. This is one way of looking for nuclear spin coupled axions. So something that is not a very difficult calculation to do, but I don't think had been done previously, is that if you sit down and say, well, this magnetic field that is interacting here is coming from a very weakly coupled axion. I mean, if it was more strongly coupled, we would have seen it already. And so this means I can actually simplify this system. And in particular, I can reduce this coupled set of first order differential equations to a decoupled set of second order differential equations. And for example, study one of the transverse directions of the spin. And this is the equation I get here, where this B, for example, is the magnetic field that is induced by the axion. So of course, this is an equation we've all seen before. It's exactly the simple harmonic oscillator. And maybe it's not that surprising that when you're discussing resonant instruments, if you're looking at them with a very weak perturbing field or driving field, which is what the axion is doing, you can reduce all of this to the simple harmonic oscillator. And indeed, this is true for essentially all of the resonant instruments that I'm aware of. Eventually, you can break the equation down into something like this here. So of course, what do we have? Well, we have the resonant frequency that we're looking at here, but there are two other important timescales that enter. The first of them is the width or the time scale associated with the response of the instrument. For NMR, this is T2, but for resonant cavity, this will be controlled by this Q factor, and whatever instrument you're looking at, there will be some equivalent time here. The other relevant time scale, of course, though, is what is the coherence time of the frequency, the system that is driving this. And so that's what's going to be entering here. This is the driving frequency, and how coherent that is going to be controlled by tau A. So you can see that both of these timescales are going to play a role, but asymmetrically. They're not entering into the problem in the exact same way. So then because I can reduce most of these problems to the simple harmonic oscillator, I know it's a problem we do in undergrad, but maybe it's worth just revisiting exactly how I solve this. T1 is assumed to go to infinity, yeah. And the reason for that is that in most of the problems we're looking at, most of the NMR cases we're looking at here, T1 is much longer than, most of the samples we study, T1 is just a much longer time. But of course it plays some role in what's going on. I'm taking somewhat of an oversimplification. And that's not always the case. I mean, I know you've been working on examples where T2 and T1 can be comparable, and then you need to add that physics in as well. But yeah, here I've just assumed it's gone to infinity. So I'm not going to go through this, but for that equation, of course, there's some Green's function we know, and I can just immediately write down what is the analytic solution for that magnetization. Of course, it will depend upon the driving force, which is the axion, and the axion's a random variable, so there'll be some stochasticity to it. But I can just simulate this many times and look at what is essentially the average behavior of this. And this is what I'm showing you here. On the x-axis, I'm showing you the time, and on the y-axis, I'm showing you essentially the amplitude of the magnetization. I've just factored out a bunch of units here. So in the case I've chosen here, this time scale is the axion coherence time, this first vertical line. And this second vertical line is T2, the coherence time of this system. And what you can see, as I start this thing to evolve, it grows, the magnetization grows linearly. And there are various ways of understanding this, but indeed, this is what occurs. At early times, the magnetization will grow linearly with time. Once you get longer than the axion coherence time, though, you can see that this system continues to grow. It does not grow linearly anymore. You can see it's fallen far short of linear growth, but it also hasn't saturated. And although this is simple, it's just studying the simple harmonic oscillator, this is a point that had been missed earlier on. In fact, there'd been some heuristic arguments written in papers saying that, oh, the axion is pushing as much as it's pulling, so everything should cancel out. And while those words might sound confusing, I don't think they stand up to just analytically solving the problem and seeing that this system still grows. I mean, once you've done this, there's various intuitive ways of understanding where this growth is coming from. But nonetheless, what you find is that you essentially get a square root growth, which is what I'm showing you here. Once the system hits the saturation time for the actual resonant instrument, this T2, well, then indeed the growth does saturate. Then the pushing and pulling argument is correct. The intuition here is this is the time scale for power to leak out of this system. And if I pump it in faster, it's leaking out just as much. So essentially I hit steady state. I mean, but again, this is just a word argument. I can also just solve the equations and I get this result I'm showing you here. So let's come back to these scalings, and maybe I won't dwell on this, but I can just quickly flash where these various scalings are coming from. So if I want to know what sensitivity I have to couplings, well, I have to be slightly quantitative about that. I want to know, for example, what is the 95% sensitivity I have, or what coupling can I achieve at 3 sigma? And the way to do this when you're looking for some oscillating field is to study just the significance will be related to the ratio of the power you have in the signal to the power you have in the background. I mean, if this was a counting experiment, the analogous formula I'd put up here would be signal over square root background. But this is not a counting experiment, so this turns out to be the appropriate test statistic. Furthermore, the power in this is essentially controlled by the field squared. You could think about that in a resonant cavity. It's also the case here for magnetization. And so it will be proportional to the coupling squared. And so that will be relevant. So let me just quickly run through where these are coming from. So in this first case here, I'm at this early times, and I showed you the magnetization grew linearly with time. So that means the signal power is growing quadratically with time. And also, if I just assume I have some white noise background, as I run longer and longer, I can integrate that over a smaller frequency range. So I can reduce the amount of background power I have to accommodate at a factor of 1/t. Taken together, this quantity will scale as t cubed, which means my sensitivity to G will go as t to the -3/2. If I'm now longer than the axion coherence time, the magnetization is still growing, but now at a square root. So I lose 1 power of t here, and this becomes t to the -1. Once I'm even longer than once I'm in the regime where the signal is saturated, but not where I fully resolved everything, what I will find is that I lose the growth of the signal magnetization, but I can still reduce the background. So I get a t to the -1/2 here. And then this final case is a bit more involved to describe. I can go through the details if there's interest, but ultimately now everything is saturated, and in the frequency domain, everything is now well resolved. So the amount of background I have is actually now decoupled from my amount of runtime. What's actually happening is that because I've now resolved the signal, as I run longer and longer, I can analyze it into a finer number of bins, and I essentially get a square root n enhancement in the number of bins I have. And this number of bins is proportional to the integration time. And when you put that in, you get a square root n enhancement to the signal power, which becomes a quarter scaling in the t to the -1/2. But I can say all these words, but you knew something like this had to happen because, of course, the Dickey radiometer equation couldn't be wrong. Yeah. So, okay, I've just solved the simple harmonic oscillator for you. So what? Is this just something you can use as an undergrad homework problem? Well, actually, it also has some implications in the search for axions. For example, if you go back to the search for axions coupled to nucleons through Caspar-Wind, this was the projections that were put back in 2013. And 10 years later, with a correct solution to the simple harmonic oscillator, the blue dash becomes the blue solid and the red dash becomes the red solid. Just to say a few words about this, what's happening down here has nothing to do with what I just told you about. At the lower frequency end, there was also some errors in the original work about the treatment of the backgrounds, which we tidied up as well, but unfortunately this reduces the sensitivity. But at the upper end, because your signal is still growing at timescales between the coherence time and T2, you actually get a larger signal than you would have thought if you didn't have that. So this is why we get an enhanced sensitivity. And there's other things, like there was a factor of 2 error in terms of the Larmor frequency here, which is why there's a shift at the top, but this is explaining what's going on. And also, just being wildly optimistic, you can see that given we've got an enhanced sensitivity here, you could ask the question of, if I built some large future version of this instrument, how could I actually reach the QCD axion? You'd have to be somewhat ambitious, but we think that the answer might even be possibly yes. And so this is a completely separate instrument that we're showing you in this solid band there.
Sorry, what do you find the band?
Oh, good. I think I mean, in this case, I don't remember off the top of my head. Yeah, surely it's not, I've got this written in my paper. Yeah. I don't remember off the top of my head. Yeah, but there's some assumption about that, yeah, which I don't remember what we've put. Yeah, no, it's a good question. I don't remember off the top of my head. Yeah. Yeah, we didn't, in this case, though, I would say we didn't make this up ourselves. We took what we'd seen done in other papers, but I mean, specifically, there is some assumption in that I don't remember off the top of my head. Yeah. To nucleons, yeah, to neutrons here, exactly, in specific. No, good question. I can look that up for you. I don't remember off the top of my head. Yes, neutrons. No, this coupling.
Has to be here. So the KCD, the capital
Is that right? It has to be exactly 0 for neutrons? Yeah. No, the band comes from DFSZ, but yeah. Anyway, I can look this up. No, fair point. Oh, Phil, please.
Just what would you have to do to realize?
So the dominant, yeah, roughly yes. The dominant noise source for a lot of this is spin projection noise, which is effectively coming from the fact that the spins you're measured are quantized. But this spin projection noise decreases as 1 over the volume. So it's been claimed if you could make like a very large version of one of these instruments, this spin projection noise will go down, and then you'll just hit the next irreducible noise, which is the fluctuations in the squid that you're reading that magnetization out through. Now, to be honest, people have had an enormous challenge building large versions of these instruments. So some people I speak to say that they're optimistic that in the coming decades, these issues can be resolved. And so maybe such a thing could exist. But really, you should think about this as if they could overcome spin projection, which maybe they won't be able to, then you could get this. Otherwise, it's going to be quite challenging. Fair question. Yeah. Oh, good. No. Yeah. Again, no. You're exactly great question. There's a lot I'm sweeping under the rug here. So this is a resonant instrument. So I look at one axion width and I analyze that for some amount of time, and then I move, and then I move, and then I move. So what we did here, we reproduced the mass range that was studied in the original papers here. And exactly what we did is we used their exact search strategy as best we could reconstruct it and said, if you did with everything we know, what would you get? So that determines how much integration time we give at any given time. And I can't remember the exact values, and although they didn't state this in their original paper, you can just compute it. How long would it take to cover this amount of mass? It takes about 50 years. So it's quite an amount of time, but it's not 50,000 years. So it's something that could be done. However, I mean, I wouldn't be wasting my time looking down here. I would be spending more time up here because I'm so far away from where I might think at least would be my approach. So I wouldn't spend the full 50 years. For this here, from memory, we just use 1 year of integration time to get this amount here. So it's a difference in integration time is the reason we did that. Very good question. Yeah. It was 1 or 5, but I think it's 1. Yeah. Good, but that's the end of this. So just to pull back, that was an aside I'm happy to go back to. But of course, the main thing I was asked to talk about was this axion background that I started out with, which was more of a new way of looking for axions that aren't the dark matter of our universe by exploiting constraints for looking for states that are. Okay, with that, I'm happy to take any questions, but thanks for all your attention.
I guess the same exercise for other experiments.
Yep. Yeah, good. Casper Electric, I can tell you. Yeah. So there's the misalignment, but we can come back to that anyway. Casper Electric, the differences are much less dramatic for 2 reasons. I'll tell you why. One, they computed their backgrounds correctly, so that was one of the biggest impacts. The second, they still have this factor of 2 error, which is the change up here. But for phase 1, you can just compute in the parameter space that they're searching here, and for the materials they were using, you were always in the regime where T2 was smaller than the axion coherence time. So the additional growth that I predicted is when T is bigger than tau A, but smaller than T2. For this particular sample, you can never enter this regime. And so you don't find that additional growth. For phase 2, you can, and that's why we get this parametric separation here, because we can get the additional growth. What is that? I don't know, and I've spoken to the authors, they don't know. So like there's a change in a slope down here, and there's nothing physical at that scale, so I don't know what happened there, but there's most of this we understand, yeah. And at least this gave us confidence that we knew what we were doing at some level, but the main reason this is not as dramatically different is because they computed the backgrounds correctly, yeah.
Why did you put phase 3?
I don't, no, we put exactly what is in their original papers. The newer things we didn't include at all. Because the main thing that we wanted to focus on here was the scalings of what's going on. Casper, whether it will be achieved, I didn't want to weigh in on, right? I think some people are very skeptical that they'll be able to achieve what they originally claimed. But if I speak to the authors, they're still very optimistic about it. I mean, the naive skepticism is the idea is 10 years old. And I think the current bounds order 6 orders of magnitude above the So they're going to need to make above the star emission type bound. So they're going to need to make dramatic improvements to do this. But I've talked to Shushkov and he's confident that it still definitely could be done. But it's certainly in some senses, as with many of these experiments, it's been harder than say, Peter and Sajid originally envisioned. Of course, building the actual thing came with a lot of challenges. So we didn't want to weigh in on that. We just wanted to, let's just redo the original calculation as like a theorist and see what actually we got out. So that was our motivation. We didn't want to weigh in on the actual realizability of this. Yeah.
Okay. For the second time, the same question. But if you go to 100 and you want to start on any say internalize or the games.
The game's more complicated. Yeah. So the naive thing I can tell you is what happens if I go up to 100 MeV. And there it's not hard to follow what we did earlier on. Because FA scaled as T reheat, it turns out your sensitivity goes as T reheat to the quarter. So you have pretty weak scaling. Like these are the improvements you would get if you went to 100 MeV. But to be honest, I think it would be, given that I don't believe the universe reheated at 5 MeV, I'd want to sit down and do the calculation where you do all of this. But we thought it was an interesting statement to do the very simple thing at the outset. Yeah, but I agree, you need to think about when you would reach equilibrium, all of these detailed questions. We just haven't done that yet. Yeah. Please.
So if you take the heat temperature,
Of course, exactly. Yeah. Well, as I was saying earlier on, I can't give you it's a function of the coupling as well. So for 5 MeV, it's 10 to the minus 7 is where you did it. But then this will change as you shift that. So, yeah.
any other questions? So, not